Let's talk about some properties of determinants. Let A be a 3×3 matrix. The first property is that if A has a 0 row or a 0 column, then the determinant of A must be 0. For this and all the upcoming properties, we will only prove for rows, because similar arguments work for columns. As usual, we will use Aij to denote the entries for A, and Bij to denote the entries for B. Now let's assume that A has a 0 row, say row I. Then Ai1 equals Ai2 equals Ai3 equals 0. We can expand the determinant of A along row I, and we get Ai1 times Ci1 plus Ai2 times Ci2 plus Ai3 times Ci3, which is equal to 0 times Ci1 plus 0 times Ci2 plus 0 times Ci3. So indeed, the determinant is 0. The second property is that if B is obtained by interchanging two distinct rows or columns of A, then the determinant of B equals the negative of the determinant of A. To prove this, we first note that this is true for 2×2 determinants. Indeed, the determinant for ABCD equals A times D minus B times C, which can be written as the negative of bracket C times B minus D times A, which is equal to the negative of the determinant of CDAB. Suppose the unchanged row is row I. Then Bi1 equals Ai1, Bi2 equals Ai2, and Bi3 equals Ai3. Since the corresponding cofactors of A and B along row I are 2×2 determinants with the two rows interchanged, Ci1 of B equals the negative of Ci1 of A, Ci2 of B equals the negative of Ci2 of A, and Ci3 of B equals the negative of Ci3 of A. Now expand the determinant of A and the determinant of B along row I. We have the determinant of B equals Bi1 times Ci1 of B, plus Bi2 times Ci2 of B, plus Bi3 times Ci3 of B. From the above, this is equal to Ai1 times the negative of Ci1 of A, plus Ai2 times the negative of Ci2 of A, plus Ai3 times the negative of Ci3 of A. Taking out the negative sign, this is equal to the negative of Ai1 times Ci1 of A, plus Ai2 times Ci2 of A, plus Ai3 times Ci3 of A, which is equal to the negative of the determinant of A. The third property is that if A has two distinct rows or columns that are identical, then the determinant of A is 0. To prove this, let B be the matrix obtained from A by interchanging the two identical rows. Then B equals A, which implies that the determinant of B equals the determinant of A. By the second property, the determinant of B equals the negative of the determinant of A. So the determinant of A equals the negative of the determinant of A, which means that the determinant of A is 0. Now the fourth property. If B is obtained by multiplying a row or a column of A by a constant k, then the determinant of B equals k times the determinant of A. To show this, suppose row I of A is multiplied by k. Then Bi1 equals k times Ai1, Bi2 equals k times Ai2, and Bi3 equals k times Ai3. Since the cofactors of A and B along row I do not involve row I, they are the same. In other words, Ci1 of B equals Ci1 of A, Ci2 of B equals Ci2 of A, and Ci3 of B equals Ci3 of A. Now, expand the determinant of A and the determinant of B along row I. We have the determinant of B equals Bi1 times Ci1 of B, plus Bi2 times Ci2 of B, plus Bi3 times Ci3 of B. From the above, this is equal to k times ai1 times ci1 of A, plus k times ai2 times ci2 of A, plus k times ai3 times ci3 of A. Taking out the common factor k, this is equal to k times bracket ai1 times ci1 of A, plus ai2 times ci2 of A, plus ai3 times ci3 of A, which is equal to k times the determinant of A. Now the fifth property. If B is obtained by adding a multiple of a row of A to another row, or adding a multiple of a column of A to another column, then the determinant of B equals the determinant of A. To prove this, suppose k times row j in A is added to row I. Then bi1 equals ai1 plus k times aj1, bi2 equals ai2 plus k times aj2, and bi3 equals ai3 plus k times aj3. Since the cofactors of A and B along row I do not involve row I, they are the same. In other words, ci1 of B equals ci1 of A, ci2 of B equals ci2 of A, and ci3 of B equals ci3 of A. Now, expand the determinant of A and the determinant of B along row I. We have the determinant of B equals bi1 times ci1 of B, plus bi2 times ci2 of B, plus bi3 times ci3 of B. From the above, this is equal to bracket ai1 plus k times aj1 times ci1 of A, plus bracket ai2 plus k times aj2 times ci2 of A, plus bracket ai3 plus k times aj3 times ci3 of A. By grouping the terms, this is equal to bracket ai1 times ci1 of A, plus ai2 times ci2 of A, plus ai3 times ci3 of A, plus k times bracket aj1 times ci1 of A, plus aj2 times ci2 of A, plus aj3 times ci3 of A. The first pair of brackets is the determinant of A, and the second pair of brackets is the determinant of C, where C is obtained from A by replacing row I by row j. Indeed, the only difference of the second pair of brackets from the first is that the entries are from row j instead of row I. So if we replace row I of A by row j, this is exactly the expression of the determinant by expanding along row I. Now, since row I and row j of C are identical, the determinant of C equals 0 using the third property. Hence, the determinant of B equals the determinant of A. Now, let's talk about a corollary of the above properties. If B is obtained from a 3x3 matrix A by performing elementary row operations, then the determinant of B is 0 if and only if the determinant of A is 0. Indeed, if we swap a row, say row I, with row j, then the determinant of B is the negative of the determinant of A, by the second property. Secondly, if we multiply a row, say row I, by a constant k, then the determinant of B equals k times the determinant of A, by the fourth property. Lastly, if we add lambda times row j to row I, we have the determinant of B equals the determinant of A, by the fifth property. So in any case, the determinant of B is 0 if and only if the determinant of A is 0. Let's look at some examples of these properties. Firstly, the determinant of 5, 3, 0, negative 1, 2, 0, 4, negative 3, 0 is 0, because column 3 is a 0 column. Secondly, the determinant of 2, 3, 4, 1, 2, 3, 7, negative 3, and 8 equals the negative of the determinant of 1, 2, 3, 2, 3, 4, 7, negative 3, 8. Because the right matrix is obtained by interchanging the first row and the second row in the left matrix. Thirdly, the determinant of 710, 4, -3, 5, and 710 is 0, because the first row and the third row are identical. For the fourth example, the determinant of 206, 123, 7, -3, 8 equals 2 times the determinant of 103, 123, 7, -3, 8. This is because the left matrix is obtained by multiplying the first row of the right matrix by 2. As the fifth example, the determinant of 305, -143, 5, -36 equals the determinant of 3014, -140, 5, -321. This is because the right matrix is obtained by adding 3 times the first column to the third column in the left matrix. Now, let's look at a definition. Let A be a square matrix. We say that A is upper triangular if all entries below the main diagonal are 0. We say that A is lower triangular if all entries above the main diagonal are 0. We also say that A is triangular if A is upper triangular or lower triangular. The following theorem is very useful. Let A be a 3×3 triangular matrix. Then the determinant of A is the product of the main diagonal entries of A. For the proof, we will only prove the case when A is upper triangular, because a similar argument works if A is lower triangular instead. Let A be the matrix with entries ABC, 0DE, 0,0F. So A is upper triangular. Expand the determinant of A along the first column. The determinant of A equals A times the determinant of DE, 0F. Notice that the remaining 2 terms vanish, because the remaining entries in the first column are 0. So the determinant of A equals A times bracket D times F minus E times 0, which is equal to A times D times F, and this is indeed the product of the main diagonal entries of A. Let's finish with an example of a determinant which can be simplified using various properties. Consider the determinant 1x x squared, 1y y squared, 1z z squared. This is called a Vandermonde determinant. To begin, we observe that the first column are all 1s, so we can subtract the first row from the second row and the third row to create zeros, and we note that the determinant remains unchanged by property 5. Now, we don't expand the determinant along the first column yet, because we see that a common factor can be taken out from the second row and the third row. More precisely, we can take out the common factor y minus x from the second row and z minus x from the third row. And this is possible because of property 4. Now, the second entry in the second row and the third row are both 1, so we subtract the second row from the third row to create an extra 0. And again, the determinant remains unchanged by property 5. Now observe that the matrix is upper triangular, so we can use the previous theorem and say that the determinant of this matrix is the product of the main diagonal entries, in other words, 1 times 1 times z minus y. So the expression simplifies to x minus y times y minus z times z minus x.